In math, you run into these incredible ideas, these beautiful, perfect concepts that seem to just stretch on forever. But what happens when you try to bring one of those infinite ideas down to earth? How do you make it actually work in our very finite, very real world? Well, that's exactly the journey we're going to go on in this explainer.
So, this is the big question, right? It's the challenge that engineers and scientists are up against all the time, taking these powerful, abstract tools and somehow grounding them in reality. And you know what? The story of the Fourier transform is a perfect example of how it's done.
Okay, so first things first, let's meet the main character in our story, the Fourier transform itself. And, well, let's also meet the massive, infinite problem it brings with it right out of the gate.
So, that integral you're looking at right there, that is the Fourier transform. It's this absolutely magnificent tool that can break down pretty much any signal into its most basic frequencies. But take a look at the limits on that integral. See that? They stretch from negative infinity all the way to positive infinity. This thing was literally designed for functions that last forever.
And boom. Right away, we've hit a pretty big wall. In the real world, you can't just work with infinities. It's like the source material says. If you try to write down infinity, it just goes a really long time. It's not practical. For any of this to be useful, the final answer can't just, explode off the page. We need a finite, concrete number.
So, how do we get around this? Well, thankfully, mathematics actually has a rule for this exact situation. It's kind of like a built-in safety rail to keep these grand infinite ideas from totally running away from us. It's a rule for reality. And that rule is all about this idea of an integrable function. Now that might sound complicated, but it's actually a really simple and crucial idea. Basically, a function is integrable if, when you add up all of its values, the grand total is a finite number. It doesn't explode. Just think of it like a shape that has a real measurable area you can calculate. If we look back at our formula, we can see the condition that makes it all work. The integral of the functions times absolute value has to be finite. What that means is, even if you flip all the negative parts to be positive and add everything up, the total still can't go to infinity. This one little rule is basically the gatekeeper that tames the whole concept. Okay, so right about now you might be thinking, hold on a second. I thought we used Fourier stuff for things like sine waves, and those repeat forever, right? And if you're thinking that, that is a fantastic question, because it gets right to the heart of a really common mix-up. So let's clear this up. We're actually talking about two different tools for two totally different jobs. You've got the Fourier series, which is the tool you use for those perfect, endlessly repeating functions. But the Fourier transform, the one we're focused on today, that's for integrable functions, the ones that don't explode, the ones that eventually die down. All right, so now that we've got that key difference sorted out, we can get to the really clever part. This is the aha moment, where a super simple practical observation lets us build a bridge from this infinite theory straight to our finite world. Just think about any signal you've ever actually worked with in the real world. A recording of your voice, a vibration reading from an engine, a little snippet of music. None of them go on forever, right? They all have a clear start and a clear end. So what if our function is only non-zero for a limited amount of time? This brings us right back to our formula and to this really elegant solution. Look, if our entire signal, our function, exists inside some boundary, let's just call it t, then everything outside that window is just zero. So why on earth would we bother integrating all the way out to infinity? The answer is we don't have to. We just need to integrate over that finite little window where all the action is actually happening. And here it is. This is the big reveal. This whole thing isn't just some neat math trick or convenient little shortcut. No, this one insight that we can just look at a finite piece of the puzzle is actually the conceptual bridge to a whole new and incredibly powerful tool. So let's just walk through that logic one more time. You start with this powerful continuous theory, the Fourier transform. Then you apply a really simple real-world constraint. My signal isn't infinite. It only lasts for a certain amount of time. And taking that one practical step is what logically leads you to create its real-world counterpart. And that new tool is the Discrete Fourier transform, or the DFT. This is the version that computers can actually work with. It's the engine that powers digital audio, image compression, so much of our modern technology. And it was all born from the simple decision to put a boundary on an infinite idea. So think about it.
We went from a mind-bending, infinite integral all the way to a practical algorithm that powers our digital lives. And it all happened just by accepting a limitation. Which kind of leaves us with a final thought to chew on. If putting a simple boundary on something can tame infinity, what limits are truly real?